Good afternoon, dear students. Our topic for today is conduction in solids. So this basically is a unit 2 of this the whole course syllabus, and you'll learn from unit 1, which is the introduction to transport phenomena, that it's all about kinetic molecular theory that offers the basis for the derivation of the three molecular transport equation, namely your Fick's equation, your Fourier, and your Newton's. But at this point, I would tell you that you forget about Fick's equation and Newton's equation for the meantime and focus your energy and your brain cells in understanding deeply what Fourier equation is, because it's the focus of this lecture. You wait until we reach unit around 8 or 7 for you to be able to encounter again what Fick's equation is in our introduction to mass transfer. But for now, it's all about Q over A equals negative K dt dx. Okay? So in this lecture, we'll be learning deeper or dig deeper about conduction, which is basically it's a transfer of heat by molecular action, or it's a transfer of energy due to either random molecular motion or due to the motion of free electrons. Included in this lecture is 4 subtopics. One is conduction as defined as the molecular transport of heat. We'll be talking about steady state conduction, knowing about Fourier equation, the evaluation of mean thermal conductivity, the evaluation of mean area, the resistance to heat flow, and we'll also be dealing with unsteady state heat conduction and how to obtain the solutions using your Fourier number and your Gurney-Lowry charts. And lastly, we'll be dealing about conduction with internal heat generation. Okay, as a start, we define what conduction is and its industrial application. I think I have here some pictures of an oven. So this picture was taken it's the actual picture that I've taken when I did my thesis during my master's. So you could see that this oven has a very thick insulation, as you could see here. And of course, one of the main reasons why you need an insulator or oven insulation is that to keep the external frame within a suitable temperature range, because without insulation, the extreme heat, this one, take a look at this extreme heat produced by the oven could travel or could affect or carry over to the frame, leaving you users vulnerable to skin burns. So thermal insulation is predominantly used to prevent heat loss through conduction in electric or gas or dual fuel models. Also, it is used to conserve energy, because as much as possible you would want a steady state inside the oven, so fluctuations of the temperature would mean greater energy usage. Okay, so just to recall, in different phases of matter, the modes of conduction are slightly different. That is, for gases, conduction is due to collision of randomly moving molecules. In liquids, although it is similar to gases, but it of course contains much smaller or mean-free path. And for solids, which is the focus of this lecture, conduction is due to lattice vibrations and or motion of free electrons. Okay, so we'll be dealing with steady state conduction. When you say steady state, there's no fluctuations in your delta T. Say for example, your heat flow is constant with time. Say your outer surface is maintained at 100 degrees C, your inner or colder end of the surface is maintained at 40 degrees. After several hours, you still maintain that same temperature. And if you recall from your equation 1.3, which is, of course, by J.B. Fourier, which is equal to Q over A is equal to K dt dx, where Q is the heat flow or the rate of heat transfer per unit time, Your K, of course, is your thermal conductivity, and your change or DT is called the gradient of the temperature. And this gradient is a measure of the rate of change of a quantity in space or slope. And the negative sign, of course, signifies that the heat flows from a higher temperature to a lower temperature. Okay? So if Q is constant at steady state, you have Q over A, or mean area, is equal to positive Km delta T delta X. So previously, it's so simple. You just have Q, your heat flow is per unit area is just equal to the thermal conductivity that you get, gradient in temperatures plus a gradient in the heat flow, or delta X. Now, we will be introducing new terms, this is your mean thermal conductivity and your mean area. Okay, as I've said, we'll only be dealing with simple geometric shapes like slab, cylinders, spheres, and frustum of a cone, and some boundary conditions. Okay, so let's take a look at how to evaluate your mean thermal conductivity, or your Km. So here, if no data is specified, you may use the K taken from Paris, Faust, or your McCabe, Smith, and Harriot using your T average. I have a screenshot here of the different thermal conductivity of various materials using Appendix D10 of your Faust. This one is for gases and vapors at a given temperature and the corresponding thermal conductivity. You can also have the liquids and some solids. Okay. Now, if K versus T is linear, you use the equation from K equals A plus BT. You use Km A plus BT average. So this came from our equation. So this usually, take note, this usually occurs in liquids and gases. So this Km equals A plus BT average is from, of course, the linear equation K A plus BT, which is, if I would separate that, I could have K dt from T2 to T1 is equal to, so if it is positive, so Km change in delta T. Therefore, if your K is equal to ABT, you have T2 to T1 of A plus BT dt, or Km, that's T1 minus T sub 2. Take note, it's T1 minus T2 because you already have a positive value of your Km here. Okay, taking the integral, I would just have A, so A dt from T2 to T1, so that's T1 minus T2 plus A plus, BT would be BT squared, right? BT squared over 2 from T1 to T2 is to Km T1 minus T2. For that, I could now have an equation of the form A T1 minus T2 plus B over 2, so that's constant, T1 squared minus T2 squared, T1 minus T2. But take a look at this. This is actually T1 plus T2 times T1 minus T2. Therefore, I could cancel out T1 minus T2 because they are all factors. So I would all be left with A plus B over 2 T1 plus T2 is equal to Km. Or, arriving at an equation, K, or mean thermal conductivity, is just equal to A plus B multiplied by T1 plus T2 over 2, and this is your T average. So that's your mean thermal conductivity if your K and T is linear. Now, how about for C? If K is nonlinear, it said we need to integrate. And nonlinearity in conduction problems arises when properties are temperature dependent or when the boundary conditions are nonlinear. Say, for example, surface radiation and free convection. These are typical examples of nonlinear boundary conditions. So although the method of separation of these variables has wide applicability, it is just only limited to linear problems. Because in solving nonlinear heat transfer problems, either you use exact numerical solutions or a two-parameter optimal linearization method. And of course, it's quite complicated. But for now, let's just stick to the first two cases of evaluating mean thermal conductivity. Okay? So this is a continuation of the thermal conductivity given in Appendix D10 for your solids. You also have in Appendix 11-13 of your McCabe. So given thermal conductivities of metals, other substances, and liquids. So in the handbook, you can just find it. I'm not just so sure with what page in the handbook. Okay, so we're done with evaluation of mean thermal conductivity. Let's evaluate mean area. So it would just be easy. For slabs, you just multiply the length times the width. If it is a cylindrical shape, or in that case pipes, your mean area is equivalent to pi L d log mean or pi L delta X ln do di. I think in the module that I have uploaded in Schoology, the derivation of these equations are found. Okay? For spheres, it's just pi RORI, and for frustum of a cone, it's just pi R1 R2. So I won't need to dwell on the derivation of these equations because, as I've said, it is found already in your module. So we proceed with resistance to heat flow. So take note that for thermal resistance, we term that as a resistance of a particular medium or system to the flow of heat through its boundaries, and of course it's dependent upon geometry and thermal properties of the medium, such as your thermal conductivity. So we define the rate to be driving force over resistance. So if our equation, from our equation, yung Q over A mean is equal to M delta T over delta X. If you rearrange, you get your heat flow to be Q by the mean area X. Now, following the definition of your heat rate, it's the driving force over resistance. Take note, what's the driving force for heat flow? It's just your change in temperature. So that, if I would have Q, driving force is your delta T. What now is my resistance? Your resistance would be your delta X over the mean thermal conductivity times the mean area. So, eto si R. This is your temperature gradient or your driving force. So, it's driving force over the resistance. Okay? So, there are just two types of resistances. One is resistance in series, and the second is resistance in parallel. So, if you have a resistance in series, it will just be very easy because your Q is equal to Q1, Q2, Q3. So whatever heat flows here, since we're dealing with a steady state, yung amount of heat rate that comes in with the first slab will just be equivalent to the one entering is the second up to third. Take note, We say it is for steady state because there would be no heat losses across the medium. Kaya nga, sabi natin, your Q would just be equivalent to Q1, Q2, or Q sub 3. And that, the summation of this, your delta T over total resistances, since it is equivalent, would just be the overall T1 minus T2 all over your resistance 1 plus resistance 2 plus resistance 3, which is different when you have resistance in parallel. So if you have a resistance in parallel, your Q is equal to Q1 plus Q2 plus Q3. So if this is your overall Q, this Q would be equivalent to the one that flows in slab 1, slab 2, and slab 3. That's why you have here your driving force over resistance, or the summation of delta T over RT, which is of course your Q, would just be equivalent to T1 minus T2 because the resistance, if you have a parallel, you have your R total would just be 1 over, or 1 over R total would be 1 over R1 plus 1 over R2 plus 1 over R sub 3. So sorry for that. So I would have 1 over for RT, your total resistance would therefore be equivalent to 1 over RT is equal to 1 over R1 plus 1 over R2. That's why if I have RT, that's 1 over R1 plus 1 over R2. Sorry for that. Okay? So that's why you would have this equation here. Okay? So we move on to a simple problem. It is given here. So by the given system alone, you already know that it is resistance. You have a resistance in series. So we have here the outer and inner surface of two glass panes with a 7 mm air gap in between are kept at 45 degrees C and 25 degrees C respectively. What is the heat loss through the window that is 5 millimeters thick and is 1 by 1.5 meters on a side? Okay, so since it is in series, you would know that Q would be T1 minus T2 over the total resistances, RT. So you need to get the resistance of the first glass plus the resistance of the air plus the resistance of the inner pane, the inner glass pane. Now, we need to get what is the resistance of the first inner glass pane. RG would be delta X km over mean area. There's no problem with the mean area. You either have it as it is already given as 1 meter by 1.5 meters. The delta X, itong area na to, of course, for the first glass pane, RG1, you have 5 millimeters. Our only problem is how to find for the mean thermal conductivity of the glass. How to do it? Ano given? If it is not given in the problem, you use the data given in the different tables. And I think I have here from Appendix D10 for the window glass. There. There's no given temperature. There's no given, this. That's for the density. What I know is for window glass, its thermal conductivity would be from 0.3 to 0.61. So if that's the case, I would therefore get Km for the glass to be equivalent to the average of the given K, or that's 0.3 plus 0.61 all over 2, which gives me 0.455. Take note, this is given as BTU per hour feet squared per degrees F feet, or usually it's BTU per hour feet degrees F. So since we are dealing with SI unit, I need to divide this because I have for every 1 BTU per hour feet degrees F, there's 0.58 BTU pala. There's 0.58 BTU per hour feet degrees F for every watt per meter Kelvin because I need it in SI. 5.8 something kasi 586 something. So let's just adapt 0.58. So that's BTU per hour feet degrees F because that's a unit of the K given in the this one given in the table. Okay, so you get that to be around 0.7845 watt per meter Kelvin. Next is for the air. In your Appendix T10, you are given at negative 148 degrees F, your K is 0.95. Meron kang at 32 degrees, 0.0140, and at 212, it's 0.013. Now, the question is, my T average is 45 plus 25 divided by 2. Convert it, so it is given in Celsius degrees, so that's roughly around 95 degrees Fahrenheit. So you need to get the mean thermal conductivity of the air at a given temperature of 95 degrees C. Since you know two values at two temperatures, 32 and 212, you interpolate. So parang you have at 32, I need the value at 95 degrees and 212, but this is 0.0140 x and 0.0183. By interpolation, you get a value of your x to be around 0.015. 0.015 BTU per hour feet squared, so that's over 0.58 to get it in watt per meter Kelvin, and you'll arrive at a value 0.02586 watt per meter Kelvin. So let's plug it here. So I have 0.015. So that's BTU per hour feet degrees F. Feet degrees F, and which gives you an answer of 0.02586 watt per meter Kelvin. Of course, there's no need for me to calculate the mean thermal conductivity of the second plane because it's just basically the same as the first. Same yung thickness, same yung property, so you would know that your Km and even your resistance for that would just be the same. So now, since I know the mean thermal conductivity of the glass, I could now compute for my R1. R1 would be the thickness, or the delta X is 0.005 meters. It's 5 millimeter thick, divided by the K, 0.7845 watt per meter Kelvin, times the mean area of 1.5. 1 times 1.5, 1.5 meters squared. So you get your resistance to be around 4.25 times 10 negative 3. For your R2, which is for the air, it's 0.007 meters. All over the km, 2586. Let's correct that one. 0, yung ba yun nandun? 02586. 02586. 2586 watt per meter Kelvin multiplied by an area of 1.5 meter squared. So you get the value to be around 0.1804. This one is basically the same with your R3. Getting R total, which is R1 plus R2 plus R3, would give you around 0.19. Knowing RT, I could now solve for finally for your Q. Q would be T1 minus T2, 45 minus 25, whether it's in Celsius or in Kelvin, just give you the same difference. All over 0.19, your R total, which gives you 105.26 watts. Okay, so that would be for your Q. Okay. Sorry. So this would be your final answer. Okay, so let's proceed with the second. Find Q where you are given already that the K1, so you have a frustum of a cone. K1 is 0.01, K2 0.2, and K3 0.03. Take note that 1 and 2 are in parallel and it is in series with your bottom, which is your number 3. Okay, so we have here, that's to find Q and T1. To get a head start, A would be Q is equal to your summation of your delta T over your total resistance, which is, that's 200 minus 25 over RT. We need to get R1, R2, R3. Okay, so let's begin with R1. So I think half of that. So R1 would be, what's the height? It's 2 meters. So that's 2 meters all over. What's the diameter? Diameter is 5 centimeters. So basically, ang half niya is 2.5. So I have K is 0.01. Wait lang. 0.01. The mean area. What's the formula for the mean area? Would be pi R1, R2, right? For the frustum. But it is just half. So ito yung half lang ang kailangan ko. So this area would be 1/2 of the pi. R1 is 2.5. R2 is 3.5. Okay. How'd you get for that 3.5? Of course, you would know that your diameter here is 8. Ito is 5 centimeters. So, by your geometry, you could solve for the diameter of the middle circle there, and you'd get here around 14.6. Your R2 would just be the same, 2 all over. This time it's 0.02 yung K2 nya times the mean area of 1/2, 2.5 times 3.5. You get around 7.3. Your R3 would be, thickness is 1 meter. So delta X is 1 meter all over. K is 0.03 watt meter Kelvin. times, since it is full, I have pi times 3.5 times 4. So the diameter is. Okay, so you get it to be 0.758. Now, since resistance 1 and 2 are in parallel, I'd apply the formula for the parallel resistance, that is 1 over R1 plus 1 over R2. So that's 1 over 14.6 plus 1 over 7.3, which gives you around 4.87. And that R1 and R2 is in series with R3, so just add. So that's 4.87 plus your 0.758 gives you around 5.638. And finally, since you know already the total resistances, you could just plug it in your original equation, 200 minus 25 all over 5.638, giving you an answer of around 31.21 watts. For you to be able to get your TI naman, your TI, since Q total is equivalent to Q12 series equal to Q of 3. So kung ito yung TI, sa gitna, I would just have your Q is 31.21 watt is equal to, titingnan ko to, I would have T sub I minus 25 all over your R sub 3. Ito yun. Take note, sorry for this location, it could just be same here as yung TI pala yung nandito. So that basically you'd end up getting TI to be 48.66 degrees Celsius. So this is how easy it is. Okay? Now, we proceed with unsteady state conduction. So here, there's a variation in the Q because Q would varies with time. So there you have here the rate of heat flow at X. Ito would be, or yung input, ito yung first na input. So since there's a gradient kanina, if it is steady state, whatever is the Q here is equivalent to Q outside. But since there's a what do you call this, accumulation or maybe loss of heat, your Q, the rate of heat flow, at X, ito, yung first, or we call that as your input, is actually equivalent to here, partial T over partial X. Yung output, your output would be your X plus delta X. This one. Of course, the Q here would travel the distance X plus your dx already, or that is your output. So rate of heat flow at X plus your delta X would be negative Ka partial T partial X. So yan yung nasa first, plus either the accumulation or your partial of partial X of the same, negative Ka partial T partial differentiation of X dx. Okay? So if you get your accumulation of heat doon dito sa areang to, it is equivalent to input minus output. And getting your equation 1 and equation 2, it would just mean Ka partial derivative of your T, the second, with respect to X squared dx. Or that is the rate of accumulation is the amount of sensible heat absorbed by the solid. get the rate of accumulation, we would define at the amount of the sensible heat absorbed by the solid. And this is equivalent to your MCP partial T partial theta. And take note that if I get my density, that is M over V, or your M times area dx, right? Or from this equation, I could get M to be area times density A dx. Okay? So if I am to substitute this in this equation, Ka is equal to your yung first equation natin, ito, second partial derivative of T with respect to x dx is equal to A times density dx, so that's your M. It's Cp partial T partial theta. Or finally, I would have let's put it here. You would have partial T over partial theta is equivalent to, so you have cancel out dx dx and then the area. So you get K over rho Cp, ito, K over rho Cp second partial derivative of T with respect to x. And this would be your equation, which leaves you that your alpha, take note, your alpha is equivalent to your, ito, diba? K over rho Cp, or your thermal diffusivity. Why thermal diffusivity? Remember before, ang sabi natin kay thermal conductivity, K is your alpha times rho Cp. Diba? Remember, your thermal conductivity, that's your K, is your thermal diffusivity times rho Cp. Okay? So, different solutions for unsteady state equation. You have requirements. One is your thermal diffusivity must be constant, or your alpha must be constant. Second is that initial concentration of T must be uniform, and that the body should be brought into a new condition which is constant with time. So we'll be using your McCabe, Smith, and Harriot using your Fourier number. You are given the equation for slab, your theta, or the time, for that would be 1 over alpha 2 Rm over pi squared ln 8 Ts minus Ta pi squared Ts minus Tb. Can you please check this in your McCabe, Smith, and Harriot? So different equations for slab, for the cylinder, and for the sphere. Okay? Take note your Ts here. So, your Ts is actually the temperature at new condition. Ta is your initial temperature. Tb is your temperature at time theta. Okay? And if you get Ta and your Tb, yung initial at time theta, you could also have the average temperature of the body. Average T of body. Okay? So parang, it's like if you have an unsteady state heat transfer, di ba? Kanina, if you have a steady state, yung different temperatures, let's say Sana steady state, if this is kept at 100, after a few hours, it lowers into 80, naging 40, tapos naging 20. So that if you get the T average for this, it should be the 100 plus 80 plus 40 plus 20 divided by 4. That gives you your T average. Okay. The second one is using your Gurney-Lurie chart. This one is from Faust naman. I think it's in page 224 of the Faust. Your X is the relative time, which is alpha, or your thermal diffusivity, times theta, or the time all over x1 squared. So you also have your Y as an unaccomplished change. So ito may makikita nyo later when we do some problems. Yung 0T is your initial temperature, T1 is the temperature at surface, T is temperature at any time and distance. Parang siya yung kanilang TB natin previously using your Fourier number. Okay? And that if you have a relative resistance, which is usually R convection, resistance due to convection over resistance due to conduction, and that is equivalent to Kx1 over H. But if there are cases that your convection is much smaller than your conduction, you assume M is equivalent to 0. Take note then for the relative position of N, say for example, ito yung first na thickness, tapos ito yung second, your relative position would be X over X sub 1. Or if you have a sphere or cylindrical, ito yung X1 mo is the radius all over, X would be the initial or the relative time given at your alpha t times theta over x1 squared. Okay, so let's have an example for that. So I think this is the modified Gurney-Lurie chart. So you are given the keys for this figure. So if I am to use figure A, ito yung reference ko. You're given M, and kung ang M mo, let's say, is 0 and your N is 0.4, you use line 5. Where is that line 5? It is roughly, this is 2, 3, 4, 6, this one. That's your line 5. Okay? This is helpful in getting your Y. Now, if this chart is not available, you will be using appendix D16, which is the extension. So for this first one is the extension of your figure A. Ito naman is figure B, tapos yung isa figure C. Okay? So what's best to learn about this Gurney-Lurie chart is to solve a problem. Okay, let's have this. A cylindrical shaft 4 inches in diameter with a uniform temperature of 1100 degrees C is plunged into an oil bath at 300 C. Now the shaft is made of steel with alpha 0.35 feet squared per hour. We are to calculate the average temperature of the shaft after 1 hour, and B, how long will it take for the solid to reach an average temperature of 700 degrees C, and find the temperature 0.8 from the center after 1 minute. Okay, let's do letter A first. You know already that your TA or your initial temperature is 1100. So TA is 1100 degrees C. The temperature at new condition, TS, would be 300 degrees C. We're tasked to get what's the temperature of the body after 1 hour. And that is your TB. It's the new temperature of the body, right? At time, 1 hour. Now, since I have here a shaft, what will I use? What equation? It is for cylinders. ang cylinder ay this equation. So, theta Rm squared. So, I'll be using an equation. Theta is Rm squared over 5.78 alpha ln of 0.692 Ts minus Ta all over Ts minus Td. Okay? You're given alpha to be feet squared per hour. So, change that into SI. So, you're given alpha is 0.35 feet squared per hour, English unit, times 0.3048. 0.3048 meters per feet squared. Squared mo siya. So, roughly get 0.0325 meters squared per hour. So, get that alpha. You know Ts, you know Ta, your Rm, or the radius. And then, you know the time at 1 hour. So, all you need to do is plug it in the given equation. So, take note that your Rm also, since you're given 4 meter, so ang radius mo is 2 inches, or your Rm would then be 2 inches times 0.0254. So, you get that as 0.0508 meters. Therefore, this equation becomes 1 hour for theta is equal to 0.0508 squared all over 5.78 times your alpha, 0.0325 meters squared per hour, ln of, so this becomes meter squared. Ito, meter squared per hour. So, this cancels out. So, hour yung makukuha mo. ln of 0.692 times 300 minus 1100 all over 300 minus your dB. And you get the value of the average temperature after 1 hour to be around 300 degrees Celsius. Okay. For the second, how long will it take for the solid to reach an average temperature of 700? So, this time, TB naman ang given, your task to get for the theta. Or, theta again is equal to, just follow, it's 0.0508 squared, meter squared all over 5.78 times 0.0325 meter squared per hour, ln of 0.692. Ts is 300 minus 1100 all over 300 minus the new temperature is 700. Get your theta to be in hours. So, at a value of 4.4645 times 10 negative 3 hours, and this actually is roughly equivalent to 16.07 seconds. So, take note, from an initial temperature of 1100 degrees, with after just 16.07 seconds, it will reach 700 degrees centigrade. Letter C. So, this is your B. Letter C, it requires us to find the temperature 0.8 inches from the center after 1 minute. So, it's like, I think I have here. Okay. So, your task to get the temperature 0.8 inches from the center. Okay. So, that would be your X. Your X would be, so using your Bernoulli chart na. So, your X is alpha, x1 squared, x is equal to your alpha times the time over x sub 1 squared. You get that as 0.0325, that's your alpha, times, and given is, that's 1 minute, or 1 over 60. So this is in hours, times your x1 0.0508 squared. So get that value to be around 0.21. So if this is 0.21, your x, you know that y would be T1 minus T over T1 minus the initial temperature, or your T sub O, your initial temperature, 0T. That is around 300 minus T all over 300 minus the initial temperature of 1100. But of course, you do not know yet the value of your y. Diba? You don't know yet the value of your y. Okay. So, I think I put the solution in this slide already. So, since you don't know y, you have to get it using your appendix D11. You assume m is 0, m equals 0, because if h is not given, you cannot really get your m. So if your m is 0, you compute for your n just to be x over x sub 1, which is your 0.8 all over your initial radius of 2 inches. So you get your n to be 0.4. Using your appendix D16, asan yung appendix D16 natin kanina? This one. So using your appendix D16 for a cylinder, you get m is 0. Ito yun. M is 0, but your n is 0.4. So itong value. You get your A and B to be, A is negative 2.511 and your B is 0.0972. So alam ko na siya that my M is 0 and N is 0.4. You get a value, A is negative 2.511, negative 2.511, and that your B is 0.0972. Using the formula, log to the base 10 of y is equal to ax plus b. You'd get the value of your y, therefore, to be 10 raised to negative ax, negative 2.5 2.511, that's your A, times the x of 0.21, ito yung x ko, plus B, 0.0972. Finally, you get the value of y to be around 0.372. Knowing your y, plug it here, this equation, so 0.372 is equal to 300 minus the temperature that is missing, which is the temperature 0.8 inches from the center, T all over TA, T1 minus the initial temperature of 1100. Finally, you get your temperature to be around 597.60 degrees centigrade. Okay? Now, I'll give you an assignment. Please do, at what time will the 0.1 inches from the surface reach 700? I'll just write it here. At what time will the 0.1 inches from the surface area from the surface reach 700 degrees C. So it's like you have here yung x1 mo, diba, 2 inches. At what time marireach na 700 1 inches. So this is 1 inches. It will reach 700 degrees C. Ang kailangan ko naman is theta. That's this. Okay? So lastly, we deal with conduction with internal heat generation. This is usually for electrical wires. Okay? So here, parang na-macro lang natin yung electrical wire. At the center, R is 0. T is equivalent to your initial temperature. You get your T1, which is R. At the surface, your R is equal to R1 and T is equal to your T1. And you have an equation of the form T minus T O equals to GR squared over 4K. Or rearranging, you could also have T minus T1 negative G over 4K R squared minus R1 squared. Take note that your G here is the rate of heat generated internally per unit volume. So it's either BTU per R per cubic foot or watt per cubic meter. Okay, let's put that into practice. Let's have here an electric current of 200 amperes is passed through a stainless steel wire having a radius of 1.27 meters. The wire is 0.91 meters long and has a resistance of 126 ohms. The outer surface temperature of the wire is held at 422.1 Kelvin. Now use a value of K equivalent to 22.5 watt per meter Kelvin. Let's calculate the center temperature. Okay? So I think meron kayong EE subject. So medyo familiar kayo. And also for physics. Go back to your physics. Okay. So initially, you have a wire. Okay? The temperature at the surface at yung T1 ko is equivalent to 422.1 Kelvin. Now, this is a stainless steel with, so ito yung Q mo, and you're tasked to find the temperature here at the center. Okay? The length is given as 0.91 meters. And pang meron, your K is 22.5 watt per meter Kelvin. You're given current I to be 200 amperes. R is 1.27 millimeter or 0.00127 meters. 0.00127 meters. This is basically your R1. So parang ito from the center to that is your R1. Sorry. So if this is the center up to the surface, that would be your R sub 1. It has to get ano ang temperature at the center of the wire. Okay? And given ka ng resistance, you're also given a resistance equivalent to 0.126 ohms. Okay? Now, let's recall from your physics and your EE subject. Resistance in ohm, diba? Resistance in ohm is equivalent to the power in watts all over your current in amperes or I squared, which is your ampere squared. Such that this would be ohm is equal to watt over ampere squared. Or if I am to get power in watts, power would be equivalent then to your current times the resistance. Okay? So if my power is equivalent to I squared R, take note, I need to get your G, your beautiful G, sorry. Ay, paano ba? Yan. Your G, I should arrive at an equation of unit of watt per cubic meter. Since I am given IR, na I and R, that would basically give me G times your pi R squared length of the wire. Okay, look at here. So you have your G, which is equivalent to the rate heat generated per unit volume, kaya nga watt per cubic meter. So your G, therefore, is your I squared R all over pi R squared L. This is in watt, this is the volume of the wire in cubic meter. Okay? So this is 200 amperes squared times the resistance in ohm of 0.0126, which gives you ohm times ampere squared is equivalent to watts, divided by your pi, radius of 0.00127 meters, times the length, pi r squared, so meter squared times the length of 0.91 meters. So that gives you watt per cubic meter. And you get a value G of around 1.09 times 10 to the 9th watt per cubic meter. Finally, plugging it into my equation, TO minus T is 1. Your T minus TO, or TO minus T1, is equivalent to negative G over 4K R squared, R1 minus R squared. So this gives me, therefore, T sub O, or the temperature at the center, T1 plus, kasi negative G kanina, so that would be plus your G R squared over 4K. Plugging it here, T1 is 422, so that's your surface temperature, Kelvin, plus 1.09 times 10 to the 9th watt per cubic meter, times your radius squared, 0.00127 squared meter squared, all over 4K. K is 22.5 watt per meter Kelvin. So you get meter, watt, cubic meter, meter squared. Finally get TO to be around 441.7 Kelvin. Okay? I think this is different from the one that I gave in the module, so at least you have additional problems to work on and to understand. Okay? So this ends your unit 2, which is conduction in solids. Thank you, and this should have been the lecture that should be uploaded yesterday, so you still have until Thursday to study about conduction. Your deadline for unit 1 module would be this coming Saturday. We'll be meeting for just a short while just to discuss the learning assessment and just give you a short quiz of what you've learned from unit 1 and unit 2. Thank you very much. Good afternoon again.